We're going to start with a little song. I think each of the panelists has got a 5-minute talk or so. But before we get into that, maybe I can ask everybody to introduce themselves. Marc, could you say a couple sentences about who you are?
Sure. I'm Marc Kuchner, and I am from Goddard Space Flight Center. I do not really sing or dance, but I do work on modeling planetary systems. I worked for a long time trying to figure out what our planetary system would look like to an eddy, and what other planetary systems will look like when we can directly image them with some kind of imaging telescope.
Okay, Jack.
Right. I'm Jack Welch from the University of California, Berkeley. Actually, whenever I come to the East Coast, it's ragging season seems to me. But anyway, I'm a professor of the graduate school. It means I've retired from teaching, but I'm still active. And work with the SETI Institute, for example, with the Allen Telescope Array for the SETI work.
Well, Paul Horowitz, you saw me yesterday. I teach at Harvard, do electronics and stuff. I think my role here got hooked on SETI in 1978. It's just too much fun building cool stuff, so I've done a bunch of radio searches going up to 250 million channel radio receivers, great project. And then Dan and Charlie Towns came along and said, hey, how about this optical stuff? So we've been doing optical SETI ever since, and our current search is an all-sky transit search with a 1,000-pixel nanosecond fast camera.
Okay, I hope we'll learn more about that. And I'm Dan Werthimer. I'm at UC Berkeley. I'm interested in SETI and the transient universe and radio astronomy in general and instrumentation. And Marc, would you start us off?
Sure. Though I'm the guy who knows the least about this stuff, I'm brand new to SETI, and my work is really sort of tangential, and I'm mostly here to learn. But if you insist, I have to kind of take this off, I guess. I brought a little video to show off A, my grad student who is now graduated, and B, what we do. I'm not sure we have audio, so I might just have to talk through it.
Well, we can put audio in.
That would be cool.
Sorry, I got the wiring rearranged.
The music's really not as good as in the previous video.
Astronomers have just begun imaging planets from outer space. The technique isn't very advanced yet, and they can't see any planets as small as those in our own solar system. But let's suppose for a moment that alien astronomers are looking at our planetary system. Could they find any evidence that planets existed around the sun, even if they couldn't see the planets themselves? The answer is probably yes. That's because at least one world in our solar system would make its presence known by its effects on a huge cloud of dust at the fringes of the solar system, in a place called the Kuiper Belt. The Kuiper Belt is a kind of cold storage zone out beyond Neptune, occupied by millions of icy bodies, including Pluto. The icy objects in the Kuiper Belt release dust that, from afar, could appear as a hazy disk at infrared wavelengths. New computer models created by NASA scientists, shown here, reveal what dust in the Kuiper Belt might look like to an alien astronomer. Neptune creates the intricate pattern. The massive planet's gravity tugs on the cloud's dust grains, nudging them in their orbits.
Neptune creates a ring structure in the dust cloud which features a gap where the planet itself resides. And this gap should make it fairly easy to tell where Neptune is from afar, even at distances where the planet is too dim to detect directly. The supercomputer simulations that Marc Kuchner and I performed also allow us to see what the dust in the solar system may have looked like when the solar system was much younger. In fact, we can go back in time and see how the distant view of the solar system may have changed.
In its youth, the Kuiper Belt contained many more objects and, consequently, lots more dust. In fact, the dust was so thick that the particles themselves often collided.
When we included collisions between dust particles, we were really amazed by what we saw.
Successively younger models of the Kuiper Belt dust cloud showed progressively simpler structure, eventually leading to a single narrow ring beyond Neptune's orbit.
Dust collisions change Neptune's gravitational imprint. The gap in the ring structure disappears. The amazing thing is we've already seen ring structures like this around other younger stars like Omaha. In terms of dust, we now know that these other systems may look similar to our young solar system.
Dust around other stars can tell us a lot about possible planets. Just as in our own solar system, it could reveal Neptune.
So in case it wasn't clear, the big new thing we did is we added collisions to the data, which is hard to do because there's a lot of dust, 10 to the 10 to the 26 something dust grains, so it's an n squared computing problem. So try squaring that. Anyway, we figured out some kind of hybrid n-body statistical technique to handle it, and that was Chris's thesis. Thanks.
Okay. Any questions for? Thanks, Mark. Any questions, comments?
So why does the Fomalhaut planet have a little hole around it like we have for Neptune and the Kuiper Belt?
What did you say? Why doesn't it have a hole? Yes.
Hole, yeah.
So that's exactly the kind of thing we explained. Thanks, Alan. So the grain collisions in a disk that's as massive as Fomalhaut's or maybe the early Kuiper Belt tend to erase the resonance signatures which make the gap. So the gap around Neptune is caused by dust that's in mean motion resonance. So for example, a dust might orbit around the sun, twice during the time when Neptune orbits 3 times. But those resonant grains tend to collide with each other more often, we found out, and the collisions are high speed and they destroy the grains. So those kinds of patterns, azimuthal patterns, tend to be removed there, and it ends up that they're removed typically when the optical depth in the cloud reaches V over C. There's some fun there's a little tiny bit of special relativity that sneaks in there.
Any other comments, questions? All right, thanks, Mark. So I've asked Jack to not only represent Berkeley, but also talk a little bit about what's going on at the SETI Institute in their SETI searches, because Seth's not here. So.
Right. Well, there's been a long program at the SETI Institute, which most of you must know about. The first part of it was the Project Phoenix, which ran from 1995 to 2004. So it was a 10-year program, and it was done at several venues with 2 telescopes in each case. One was in Parkes, in which the main telescope that was used to receive was the Big Parkes telescope, and the secondary one for checking things out was the Moffett telescope a bit to the north. Another venue was the 140-foot here was used, along with the Woodbury telescope. A little bit to the south of this is the checking telescope. And then maybe the most fancy one was Arecibo with the Lovell telescope. And it's possible using 2 widely separated telescopes to use this kind of pseudo-interferometry to see whether or not what's coming in is really coming from off the Earth. And so that was a big program. And altogether, observations were done in what was termed as the water hole, 1420 to 1720 H to OH, covering that band. And altogether, I think there were 3,500. Let's see, this is a 300 megahertz band. I think there were altogether 1,000 stars observed, with an average bandwidth of 300 megahertz. So it was a big program. And that came to an end. And the next point was what to do from there. And on the basis of a program that the Institute put together to study what would be a good direction to go, it was decided to build the Allen Telescope Array, essentially. There was quite a long discussion of how it would be done, and that would be one of its main things. The plan was to do this jointly between the SETI Institute and UC Berkeley. And the idea there is that the SETI work will go along probably for a long time, not getting the steady usual kind of result that one expects to get in astronomy. And other astronomy could use the telescope for some of the time, and that could support it. So that's been underway just in the last year and a half. And by now, the extent of the program is about equal to what was done in the Project Phoenix. And coverage is, again, in this region around the water hole, but it's actually a little larger than that, somewhat more, 1 to 3 gigahertz. And that's an ongoing program. And there's some subsections of that. The Galactic Center was surveyed over some 3,500 points. Exoplanets have been looked at in those directions. And then there was a raster scan around Cygnus X3, and a frequency range, which was pi high, pi times the hydrogen line, was surveyed for about 92 stars. So that's the way the program is flowing on from now. I have some other ideas about the direction we're going with it, but maybe that's enough for the moment.
Okay, we can come back to that
Yeah.
if you want. Well, I just want to add a few words, because Jack is a modest guy. So this ATA, the Allen Telescope Array that Jack was talking about, is a pioneering new way to build radio telescopes, and Jack was one of the principal designers of this spectacular thing. And the idea is to build a big telescope out of lots of little telescopes, because you can stamp them out like hot tubs. They're cheap, and it wasn't really possible in the past because the electronics cost is dumb, and they figured out a way to make them very inexpensively. And I think this is the way that all radio telescopes will be built in the future, and it's the kind of the main model now for the square kilometer array. This thing with thousands and thousands of dishes. It'll be built either in South Africa or Australia, maybe in the USA for the high frequencies. And Jack was one of the leaders of that effort, and Jill as well, who made that thing happen.
You know, actually, one other point should be mentioned. It's a very wideband system. Now works continuously from 5.5 gigahertz up to 8 gigahertz. And there's a plan to increase that, and I'll talk about that a little bit later. But it's basically a very wideband instrument. It works over many octaves simultaneously. And the goal is going to be able to study the whole band. We're looking forward to getting 1 gigahertz to 15 gigahertz continuous operation, and we're pretty sure we can manage the analog part of that, bringing the whole signal back. And then it's going to be a job for people who know about digital stuff to be able to digitize that whole band. So we're looking forward to having the capability of observing in that entire band all the time and look at many little spectral elements in it. This is the sort of thing we feel is really going to be essential so that you get good coverage when you look at any potential direction.
Yeah, and our group is working on digitizers that can digitize at 26 gigasamples per second. We haven't quite figured out how to process that data yet, but I think that this design of this telescope is designed for Moore's law, anticipating that eventually we will be able to process that bandwidth. Oh, okay. Thanks, Jack.
So how many Ozmas is the Allen Telescope Array when it gets fully?
I don't have the conversion factor.
It's almost 15 orders of magnitude.
Wow.
It's I think these things it's hard to compare because there's lots of different pros and cons of these different telescopes. The ATA is really spectacular. When you have these small dishes, you can look at a very wide field, so you can do surveys very rapidly. Other dishes have more collecting areas, so they're more sensitive, you know, these big things. And I think what I'm really excited about today is that there's a lot of orthogonal searches. Some are very sensitive, some are wide field, some are sky surveys, some are targeted, different wavelength explorations, different kinds of signal types. That's very different from the early days of SETI. And I think it's actually, it's hard to just say, oh, we did so many Ozmas, or we did, you know, I think it's hard to compare these searches now because there's such a rich variety, which I think is wonderful. And I think we'll hear about some of that variety from Paul, who's doing something very orthogonal. But are there any other questions? Yeah, Jay.
Yeah, I've got a question, but this may be a little premature. In a few years back, using very conventional means to look for pulsars, Doug Lorimer found this isolated pulse that he attributed to some energetic event at a very great cosmological distance. And I just saw a paper a few weeks ago by people going back and analyzing all this data from Parkes who suggest that it's actually a phenomenon in our atmosphere.
Yeah.
And that something, there's a lightning sort of thing. And so, has this shown up in SETI searches?
I'm actually going to talk a little bit about that, and Andrew Simeon has done a lot of this work back there. Just to kind of reiterate, this phenomenal thing from more than 1 billion light years away saturated the amplifiers of the Parkes telescope. You know, incredible energy. Nobody knew what it was. And cosmic strings, primordial black hole. There was huge speculation, I think most astronomers that are close to this now think that it had nothing to do with an astronomical event, that it was interference or an atmospheric phenomena. And the reason is that they had this filter on that said if you just see it in one place, one beam of the 13 beams, then let me know about it, you know, ring the bell. And then a graduate student turned off that filter and found a whole bunch of these things that were happening in all the beams at roughly the same dispersion measure. They're very similar, not exactly similar, but there's a bunch of these things now. And so they're not exactly sure what they are, but it seems extremely likely that it had nothing to do with some astronomical phenomenon.
I guess my question in a larger sense is that there have been thousands of hours spent on radio SETI searches.
Right.
Have you found any phenomena?
So I'm going to talk about some interesting candidates there. I would say that the data that we've taken for SETI has been very useful at mapping the galaxy and finding structures. It's put lower limits on the number of these. We right away, early on, Andrew can talk a little bit about this. We're able to put interesting limits on the number of these kind of Lorimer things and kind of ruled it out from this experiment that we did at the Allen Telescope Array, where we looked at a very large field of view. We pointed each telescope in a different direction. And then at Arecibo, we did similar searches, and other people did these searches and kind of ruled it out. So we have interesting limits on the number of primordial evaporating black holes. We have kind of lower limits on that stuff. Yeah, the main stuff we've done is galactic structure work with Carl Hylas, using that SETI data to do sort of standard astrophysics. Some pulsars, some kind of, there were other kind of spin-offs from instrumentation and distributed computing, but I think that was the main astronomy spin-off.
What was the date of that event?
It was announced 2.5 years ago, but the data was quite old. It's 5 years old.
Well, I mean, the reason I ask is you're putting a very special filter on the universe, and it's tuned for intelligent life, but there's other stuff that may fall through that filter.
Yeah, and I think it's an interesting point, and I think the early SETI searches were looking for signals that were compressed in frequency, a narrowband signal. And now our group and other groups are starting to look for signals that are compressed in time, which is equally sort of interesting. It's a non-natural sort of event. These nanosecond kind of pulses, like the Lorimer burst that you were talking about, could easily come from, and Earthlings are now moving, and some of them are moving in that direction towards spread spectrum communication, pulse communication, high bandwidth kind of pulse stuff. And maybe advanced civilizations do that. And I think it's kind of equally likely that other signals, whether they be artifacts or deliberate signals, could be these in the form of pulses rather than these narrowband signals. Yeah, Woody.
If I could just chime in, the late NASA program that was going to do an all-sky survey over the entire 1 to 10 gigahertz range had done various calculations and speculations about that there might be some very useful astronomy that would come out of that, and many of us were convinced that it probably would. Unfortunately, that never took place. It seems to me it was more likely to have this kind of serendipitous astronomical discoveries than the targeted star survey, which was able to go forward with Project Phoenix. But now with your broadband capabilities, you may well discover some interesting lines, who knows, from an axion or something that pops up that would be serendipitous at the ATA.
Yeah, and let me add a little to that. What we now have is 4 filters, each of 100 megahertz, that we can tune anywhere in the band. And that's all we can manage as far as the back end goes. But the digital activity is going very rapidly, and we know how to produce an analog band 1 to 15 gigahertz that we could use entirely. That's a development we're going toward. And our expectation is that we'll end up digitizing that whole band. And so you'll be able to look at in whatever you want to look at in every direction, seeing the entire 15 gigahertz, which is kind of the radio window, all of it, and over a spectrum with many pixels in it. And that I think is the kind of moment when we really have to start getting somebody, hearing something, because wherever we point, we could get just about everything you could hope to get out of that. So that's the direction we're going with. And it's going to, we know how to do the analog part. And we're waiting for people like Dan to digitize the 20 gigahertz.
It's taking so long.
Woody, when we do the 20 square degree survey of the galactic plane, which we're now doing, the radio astronomers actually have a commensal project on the back of that, which looks for transients.
Mm-hmm. You mean transients in time? Are you looking for weird spectral lines also? Unexpected spectral lines?
We're looking for anything that's in the bandwidth that we're observing at the moment.
Yeah, okay, well.
Other questions or comments?
I mean, just to point out that there's no amount of bandwidth that you can add to the fundamental limitation of many of these searches is between our ears. That the bandwidth between our ears is more important than the bandwidth that we can put on the back end of a receiver. And the history of astronomy is filled with examples of discoveries made because some poor graduate student didn't have a filter between their ears. And, I mean, for example, for years at Arecibo, you look at a pulsar spectrum and the red noise dominates. So no one did pulsar searches for slow period pulsars. And now magnetars are a big deal. And so used to chop out the red part of the spectrum. Similarly, at the high end of the spectrum, of course, with Don Backer and Sri Kulkarni's work. So I think our ability to find these new phenomena that Jay's talking about is really limited by our ability to anticipate those phenomena.
Yeah, I completely agree, and I think SETI is likely to fall into that category, that it will be a glitch in somebody's data, not necessarily a SETI experimenter. I think half of the really interesting discoveries in radio astronomy are serendipitous discoveries, and so we need to be on the lookout. Data mining kind of searches are very interesting in SETI, I think. So, any other thoughts on that? Okay, well, let's move on. Paul?